All right, so we've got our pirate goes up 7. Now I used scale, right? I used centimeters here, so I went up 7 centimeters and to the right 4 centimeters so that I have those directions in there, but I'm going to just label it as well. So we've got 7.0, miles north and 4.0 miles east. What's my displacement overall? So in order to get an overall displacement, I'm going to draw the line from our origin to the end of our vectors. Right, so we went up first and then to the right. And so my question is, what is my overall displacement? How far did I travel from where I started to where I ended? So how are we going to solve this? Pythagorean theorem, right? A squared plus b squared equals c squared. So we could do that. A squared plus b squared equals c squared, but since we're solving for c, we'll just take the square root of those two.
Comes out to like root 65.
Yeah, but we can do better than that because we don't like irrational numbers like that. So we're going to find out what that value is. So we've got, what is that, 49 plus 16. So the square root of 65. And that's going to be, so it's going to be 8.1. Now, that is a measurement. So what is it measuring? What unit? Miles, you got it, 8.1 miles. Awesome, 8.1 miles. But that's not a vector. Northeast, but here's the trouble. Northeast could be anywhere in this quadrant of a graph, right? Anywhere in that whole quadrant. So that's not specific enough. We got to be more specific than that. Is there a way we can quantify how far over it is? Yeah, we could find that angle, right? This angle right here, we could find theta. Opposite over adjacent, but if I just do tangent, I need an angle to run my tangent function. I'm going to use, the inverse. So I'm going to say tan -1 of, now that ratio has got to be opposite, so 4 over 7. And that's going to return me 60 something, right? No, 20.
29.7.
Cool. 29.7. Could we be? Let's go to
744.
744. So let's say 74. Angles have their own sig fig rules. I don't want you to have to learn new rules. And since like 0 is a legitimate angle measure, right? Let's just keep it 2 spots after the decimal for angles. Okay? So we'll leave 2 spots after the decimal for angles. Great. So now I can report 8.1 miles at, here's the thing though, 29.74 degrees goes with this angle. So I have a choice. I can either say 29.74 degrees. Now look at this. See how this angle is measuring where the red line is compared to north? So I would have to be facing north and then turn east 24.74 or 29.74 degrees. So that would be 29.74 degrees east of north. I would be facing north and then I would turn east that many degrees. But I find that tricky. It's better if you just draw it and say theta equals that, right? I'm okay with that. I'm also okay with generally solving for the smaller angle. But you're going to get some professors or some teachers who are going to want you to stay like the unit circle, measuring the angle relative to the horizontal, to the x. So in that case, if that's alpha or so, we might have to answer that way. Subtract it from 90, great. Or I could just flip my ratio here. Because here's the cool thing about vectors. It doesn't matter the order that you add them in. For instance, let's say instead, if it were feasible, depending on where this treasure was, what if I went 4 east first and then 7 north? Wouldn't that get me to the same spot? Right, so it doesn't matter the order I add them in. Have you guys, you ever been to an airport, like a big airport, and you know how they have those like moving walkways, like the people movers, right? Okay. I want you to imagine you're on the second floor of an airport and you're looking down and there's one of those people movers. And do you guys know what a Roomba is? Those little vacuums that like go on their own. Imagine a poor little Roomba got trapped on one of those people movers. All right, so there's the people mover, and the Roomba is like bouncing back and forth between the posts of the, like the walls of the walkway. Now, at the same time, that people mover is moving to the side, right? So it's moving this way. Let's use a straight edge here. So let's say this is a spunky little Roomba. It's got a lot of speed to it. Spunky Roomba. So in this direction, it is going, what did I want to say? 5 point something. Let's pull this over here. 5.4. Let's call that meters per second. Spunky. And sideways, it's moving 7.8 meters per second. Now, in the first problem, the pirate had to go one direction and then another. But in this problem, these two things are happening simultaneously. Do you see how I represented that by starting at the same origin and moving out simultaneously? Okay, so that first version is called tip-to-tail method. All right, this is called origin method. All right, so we're going to do both of these at the same time. Sometimes this is also called the parallelogram method. Before I show you what we're going to do, can you take a guess at which way it's going to appear that this Roomba is moving? Yeah, in that top right diagonal along that quadrant number 1. So this is called the parallelogram method. I'm going to make a parallelogram out of these two vectors. I'm going to take this vector and I'm going to copy it and paste it right on top like this. So now I got a dotted line up there. And then I'm going to copy and paste this vector right over there. So it's going to look like this. And now I'm going to draw a line from the origin to the opposite corner. Like this. Now here's the thing, in that first problem, up here, I took great care to measure out 7 centimeters up and 4 centimeters across. So ideally, I should be able to use this to see that that's a little bit more than 8. I don't know if you could see that, but it's a little bit more than 8. Right? And because I did that to scale, I could also use a protractor to verify the angle there. I don't know if you could see that, but it's just shy of 30. You can't see that, but it is. It's just shy of 30, and we thought it was going to be 29.7, so that's sweet, right? But down here, I did not take such care. I just drew lines of indiscriminate length. I mean, roughly. But I can't measure out that value. So let's do a little math. How am I going to find this magnitude, the magnitude of that red line? Well, so now, wait. Pythagorean theorem, right? Pythagorean theorem would help me find that value. So I'm going to use the Pythagorean theorem there. So I'm going to say a squared plus b squared, taking the square root of it, equals c. So we plug those in. Doesn't really matter what you choose. I'm going to do 5.4 squared plus 7.8 squared. Take the square root of that, and what do I get? 9.49.
Yeah.
Okay. So 2 sig figs, 9.5. Now that's zipping. All right, that's moving pretty darn quick. Before we do anything else, I want you to notice that because there are kind of two sources of energy, right? There's the Roomba moving up and the people mover moving it sideways. Because of that, I'm moving faster than any one of these two vectors on its own, right? Moving diagonal, I'm moving faster than either of the individual pieces by themselves. Okay? And that's true for boats going across a river with a cross current. It's true for airplanes flying through the air with a crosswind. And it's true for surfers who are riding down waves. They're using gravity to slide forward, but waves usually come in diagonal. So they're riding those diagonal waves, moving a bit faster than they would if it was just gravity or just the wave. Okay, so there's that. Next thing, I've got to solve for an angle. All right, so let's choose this angle right here. All right, so that angle right there, what function am I going to use? All right, so we're going to use that inverse tangent. Now, wait a minute. This is opposite over adjacent. I don't have a value here for this opposite side.
Yes, you do.
Or do I? Right? Because this is a parallelogram, meaning that opposite sides are parallel and therefore congruent. And so that opposite side is going to be 5.4 just the same. And so what is my theta? 34.69?
695.
So let's just call it 7 for the moment. 34.7 degrees. Awesome. Sweet. So this process that we just did twice now, this is called vector addition. I'm adding vectors together. Now, sometimes vector addition can be even simpler. Let's take, for instance, that 7 and 4 like we had at the beginning. Let's say I have something that is, I'll use some different colors here to make this more fun. Let's say I have something that's 7, and I've got something here that's 4. And I add them together like that. Isn't it clear that they'll total up to 11 in that direction, right? So these arrows act like vectors, right? They're stand-ins because they tell you direction based on the pointiness, and they tell you a magnitude if they're drawn to scale or if they're labeled, right? So it gives you magnitude and direction. That's awesome. So I can add them that way, and it doesn't matter if it's this way or that way, right? Because my arrow will take care of my signs, right? I can also add them. What if I have, let's start with 4 in this direction. But now I've got 7 in this direction. You got it. So it's essentially asking which way wins and by how much. It's this way by 3. Okay. What's happening? Yeah, would you sign out, sign in? So you can see that when I'm adding these two vectors, I can get a value that's a maximum of traditional addition, 11. I can get a minimum of traditional subtraction, which is 3. But I can also get values in between, including 8.1 or any others, depending on how these are arranged. Right now they're arranged at a right angle, right? So I'm going to get that hypotenuse. But I could change these angles and get all values in between. Okay? Cool. Okay?
That what we said it's moving 9.5 meters per second, 34.7 degrees north of east.
You could say that, yep. In this particular problem, it doesn't say directionally like north or east. So it's a good habit to get into to solve for from the x-axis.
And just let it sit there.
Drawing it helps out too, right? Because that way I can see, okay, you solve for theta, there's theta, okay? Or the smaller angle. Really, it ends up depending on what your college professor wants you to do. Okay. If you were directing a horror movie about giant flying turkeys, where would the scariest shot be?
Which way to go?
Does that say 38?
38. Yeah, I would say right below it because this turkey is not wearing a diaper. Okay, so here's the question. If I've got a truck down here, and that truck has a little camera on the back, how do I know how fast I have to drive? Well, I know I want to stay directly underneath that turkey, right? So to solve for this x-axis, is this line adjacent to or opposite of that value, that angle?
Adjacent.
It's adjacent, so am I going to use SOHCA or TOA?
Cut. See cosine.
I'm going to use my cosine, right? So if I'm solving for this line here, I'm going to use my cosine, and I'm going to draw in, well, my regular equation is cosine of theta equals adjacent over hypotenuse. But I know my hypotenuse. I'm solving for adjacent. So how do I get adjacent to be isolated on that side? What do I have to do?
38.
Multiply both sides by hypotenuse. So in this case, it's going to be 38 times the cosine of 55 degrees. What's that going to equal? 21.80? Okay. Well, you know what? I got 2 sig figs and 2 sig figs. Let's call it 22. Because really, whose speedometer goes down to decimal places?
Cool people.
I suppose. Right? Our speedometer can only measure so well. So let's keep that at 22 meters per second. That should keep us right underneath the turkey. Gobble, gobble. But there's more to this problem. Well, not how high, because we're breaking apart a velocity. So it's how quickly does it gain altitude. Now, if we're filming this inside in a warehouse or something, that's going to be really important information. Now, I don't know if you noticed this, but I tried to keep this up and down, same as this side to side, right? I essentially made an invisible parallelogram around that vector, around that red vector. So I want to know what is this vertical value. So what trig function am I going to use here? Going to use sine, right? So I'm going to use sine of theta equals opposite over hypotenuse. But again, I got to get rid of that hypotenuse. So I'm going to type in 38 times the sine of 55 degrees.
Wait, why are we using sine?
I'm trying to solve for this vertical value.
What
Eh,
angle are you using?
Sorry, say it again.
What angle are you using? The
55?
degrees? Okay.
Same one, because it's essentially the same as this line right here. Because it makes a parallelogram where opposite sides are equal. Okay. So what do I get here? .31 meters per second. Okay. Couple of pieces of information we got to keep in mind here. First of all, make sure your calculators are in degrees. We'll get to radians another time this year, but right now make sure you're in degrees.